Hello, my name is Paweł Gora. I'm the founder and CEO of the Quantum AI Foundation. We are a charity organization aiming to support research, collaboration, and education in new technologies, especially quantum computing and AI. I'm also the board member of QWORD and coordinator of its local Q cousin, Q Poland. So our goal is to build an open ecosystem in quantum technologies. And today I will give a talk about quantum machine learning. So first I will give an introduction to quantum computing, and later I will tell how quantum computing may enhance machine learning and vice versa. So let's start. What is quantum computing? So the simple answer is that these are computations according to the laws of quantum mechanics. So now the question is what the quantum mechanics is, and it's not easy to answer. So let's try to explain what does the word quantum actually mean. So in physics, a quantum is the minimum amount of any physical entity involved in an interaction. And the fundamental notion that a physical property can be quantized is referred to as the hypothesis of quantization. This means that the magnitude of the physical property can take on only discrete values consisting of integer multiples of one quantum. So why it's important? When we analyze algorithms, we can analyze their complexity, try to prove their correctness or some other mathematical properties. But at the end of the day, we would like to implement our algorithms and run computations on a physical device. And this physical device is governed by the rules of the physical world, which is inherently quantum. We know it since the beginning of 20th century. So this is the time when the quantum mechanics started as a new domain of science. Everything started from the Max Planck's postulate, which basically says that the electromagnetic energy could be emitted only in quantized form. So the energy of a photon or electromagnetic wave is proportional to the frequency of this photon or electromagnetic wave. And as you can see, there is a Planck's constant and there is an integer number. So assuming that the frequency of a photon or electromagnetic wave is a constant, the emitted energy can be just proportional to this constant, right? So we cannot emit any arbitrary values of energies. One of the consequences is the Landauer principle, which says that there is a minimum possible amount of energy required to any logically irreversible manipulation of information, like erasing one bit of information. And in this case, we have the Boltzmann's constant and the temperature of the environment. So we can do computations on physical devices, but we cannot do it for free. We have to use some amounts of energy. There are some limitations. So the question is, what are the limitations of computers? We can observe miniaturization of computer elements, and even Richard Feynman realized that there's nothing that he can see in the physical laws that says the computer elements cannot be made enormously smaller than they were in 1960s. Indeed, more than 60 years ago, the computer elements were much bigger than they are nowadays. So we can observe that the computer elements are getting smaller and smaller. We can observe the trend that's called the Moore's law, that the number of transistors in a dense integrated circuit doubles about every 2 years. And this prediction proved accurate for several decades and has been used in the semiconductor industry to guide long-term planning. But even Moore himself realized in 2015 that this law is dying, right? And also the Intel company working on processors realized that the pace of advancements has slowed. So now this doubling of density is not once per 2 years, but once per more or less 2.5 years. But it's expected that the trend will continue thanks to hyperscaling. And now the question is whether this trend can continue forever. So assuming that this trend will continue for the next 15 years, About 2035, 2040, the size of a single transistor should be of the size of a single atom. And in such a scale, the transistors will not, or shouldn't, will not be able to work exactly the same way as they work nowadays. So in such a scale, transistors will not be able to just operate as they operate nowadays, because they will be governed by the laws of quantum mechanics. So how we can run computations in such a small scale? Again, Richard Feynman, one of the fathers of quantum computing, said that he can imagine that our data are represented by a row of atoms, with each atom in either of the two states, and that's our input. And then this quantum system may evolve according to the wave function, the Schrödinger's equation, and finally we can get and read the answer. And he said that nothing could be made smaller, nothing could be more elegant, no losses, no uncertainties, no ever-ranging, but the question is, can we do it? So since we have a lecture about quantum machine learning, we can expect that, yes, we can do it. And indeed, there are already some quantum processors. Here we can see Bristlecon, which is one of Google's quantum processors. And on the right is a cartoon of this device where each X represents a qubit with nearest neighbor connectivity. So what's the difference between classical computers and quantum computers, as we know that both exist? In case of classical computers, we have bits and classical gates. Bits may have one of two possible states, 0 or 1, and these values can be just an input to classical gates like AND or NOT, and these classical gates just produce the output, which is again 0 or 1. In case of quantum computers, we have qubits and quantum gates, and they operate differently. And because the state of a qubit may be the superposition of states 0 and 1. So even mathematically, this superposition is something much more complex than just a set of 0 and 1, as it was in the case of bit, because it's a unitary vector of the two-dimensional Hilbert space over complex numbers. I will try to explain how and give some intuitions how we can think about it. Another difference is that in case of classical computers, the state is determined, so we can know exactly whether the state is 0 or 1, and we can change the state from 0 to 1 and vice versa. But in case of quantum computers, to get values 0 or 1, we have to do a measurement which breaks superposition, and the probability of getting 0 or 1 just depends on the state of the qubit. So it depends on this unitary vector. And quantum gates can just modify qubits. And this probability, of course. So here we have the illustration of a quantum superposition. We have two basis states, 0 and 1. So these brackets just represent the so-called bracket notation or Dirac notation. We can think about 0 and 1 in this case as an orthonormal base of a quantum system. So two-dimensional vectors like 1, 0 and 0 and 1. So any orthonormal base in two dimensions, but this space is over complex numbers. So A and B are complex numbers, such as the squares of their amplitudes are probabilities of getting 0 or 1 in a measurement, so that the sum of the squares should be equal to 1. From the theory and arithmetics of complex numbers, we know that we can represent each complex number as a multiplication of a module, and e to the power I phi, where phi is the so-called phase. So by calculating sinus and cosinus of this angle, we can get the exact values for this complex number. And only the relative phase between the coefficients of the two basis vectors has any physical significance. So the phase of the quantum system is not directly measurable. So the implication is that by multiplying these coefficients A and B by a unit vector, we do not change the quantum state, in fact. So we can just multiply both A and B by conjugate of A, and then we can get a real value in front of the state 0. So thanks to this, we can transform these parameters a and b to spherical coordinates. So instead of having two complex numbers, we may just have two angles. So values from the range from 0 to pi or from 0 to pi. And thanks to this representation, we can interpret that the quantum state is just a point on a sphere that is called a Bloch sphere. So state 0 and 1 are just antipodic points on this sphere, but the quantum state can be any point on this Bloch sphere. So sometimes it's also said that quantum computing, at least in the case of a single qubit, is just a journey on a Bloch sphere. Because, as we'll see, quantum gates just correspond to rotations of this Bloch sphere. So here are just examples of quantum gates. So there are some notable examples like Hadamard's gate, X Pauli gate, Y Pauli gate, Z Pauli gate, and CNOT. So CNOT is a quantum gate operating on 2 qubits, where 1 qubit is a controller for the NOT operation, or X Pauli gate on the second qubit. So you can see that X Pauli gate is this quantum negation because state 0 is transferred to state 1 and state 1 to state 0. In case of the Hadamard's gate just serves to transform state 0 and 1 to superposition of state 0 and 1, in which the probability of getting 0 and 1 after the measurement is the same, it's 0.5. All right. For each quantum gate, there is also a matrix representation. So in the case of Hadamard gate, we have the Hadamard matrix. It's also good to know that the Hadamard gate corresponds to a rotation of pi about the axis x plus z, or alternatively p over 2 around y axis and then p around z axis. So these are just transformations, rotations of the Bloch sphere, as we said. Since we interpret 0 and 1 as two-dimensional vectors, we can also easily describe how these vectors are transformed thanks to this Hadamard matrix. It's similar for the X Pauli gate. So in this case, it's a rotation of pi about the axis x. It's similar for gates Pauli Y and Pauli Z. There are also some other rotation gates in which can be parameterized. So instead of rotating just by a constant angle like pi, we also may rotate by a specified parameter. Especially such gates find applications in quantum machine learning. I already told about the CNOT gate. So it acts on 2 qubits and performs the NOT operation, so X Pauli gate, on the second qubit only when the first qubit is 1, and otherwise it leaves it unchanged. The true power of quantum computing comes with quantum parallelism, and when we have more than 1 qubit, in fact. So as in this case, when we apply the Hadamard's gate to all n qubits, we can get the superposition of all possible 2 to the power of n bit numbers, or quantum states representing these n-bit numbers, in fact. So then we can apply some other quantum gates and just modify the probabilities of obtaining one of those 2 to the power of n numbers after the measurement, but we can represent all possible 2 to the power of n bit numbers on n qubits. And it's an interesting advantage comparing to classical computers. So here is an example. So it's a simple quantum circuit prepared using IBM quantum experience framework. We have 8 qubits, 8 quantum registers from Q0 to Q7, and 8 classical registers on which we save the results of measurements. So in case of 3 qubits, Q3, Q5, and Q7, there's no gate. So initially all the qubits were in the state 0. So after the measurement, we also obtain 0 with probability equal to 1. In case of qubit number 6, there we have X Pauli gate. So we change the state from 0 to 1, and with probability 1, we obtain the value 1 after the measurement. An interesting case is with the gates 0, 1, 2, and 4, because in the case of the qubit 4, We first apply the Hadamard's gate, and then we have 3 CNOT gates, which entangle our qubit number 4 with qubit 0, 1, 2, where qubit number 4 is a controller for qubit 0, 1, and 2. And then we apply again the X Pauli gate to qubit number 4. So what happens here? Initially, the qubit number 4 was in the state 0, but after applying Hadamard's gate, it was in a superposition of states 0 and 1. So just to recall how state 0 is transformed, superposition of state 0 and 1. And the probability of getting 0 and 1 after the measurement would be the same. But at the same time, we entangle this qubit with 3 other qubits and then apply X Pauli gate. So in this case, qubit number 4 is a controller of qubits 0, 1, 2. So when we obtain a value 1 after the measurement, in the case of qubit 4, with the probability 1, we should obtain values 0 in the case of qubit 0, 1, and 2, and vice versa. If the results of the measurement in the case of qubit 4 is 0, and the probability of such a result is 0.5, then with probability 1, the results of measurements on qubits 0, 1, 2 should be equal to 1. So with probability 0.5, we will obtain the results of a measurement equal to 0, 1, 0, 1, 0, 0, 0, 0, just by reading values of qubits from qubit number 7 to qubit number 0. And with the same probability, we'll obtain the value 0, 1, 0, 0, 0, 1, 1, 1. So these 8-bit numbers are just ASCII code representations of my initials, so upper case letters P and G. So this was just an example of a simple quantum circuit, but it also shows that on n bits, we can process only one n-bit number at the same time, but in case of n qubits, we can process potentially all to the power of n-bit numbers at the same time. So in the example that I showed, on 8 qubits, I was able to represent 2 8-bit numbers at the same time, but there is a potential to represent all 2 to the power of 8 8-bit numbers. Another interesting property of quantum computers is that we may have real randomness, and we can easily sample from probability distributions, which are difficult for classical computers, like Boltzmann distribution, for example, which also find applications in machine learning. In case of classical computers, we rather have pseudo number generators, and so results are rather deterministic. Okay, so what are the applications, potential applications of quantum computers? So first of all, quantum cryptography, like breaking classical cryptography algorithms, or solving combinatorial optimization problems which frequently occur in AI, finance, transport, logistics, sampling from difficult distributions like the Boltzmann distributions, simulating quantum processes, which may find applications in discovering new materials or new drugs. So going to quantum machine learning, I've already encountered many variants of quantum algorithms for almost all popular classical machine learning algorithms. So we may have quantum neural networks, quantum SVMs, quantum GANs, quantum reinforcement learning. So there are really many articles, many papers. And when we talk about quantum machine learning, it's good to know that in general, there might be several approaches to do quantum machine learning. So potentially you can apply classical machine learning algorithms and operate on classical data to just discover some interesting properties of quantum systems. Also, we can get some quantum data from some quantum experiments and do apply some classical machine learning algorithms. So there is a domain that is called quantum tomography that is very interesting. Also, we may have classical data, but we may apply quantum algorithms to operate on those data. And this is also a very large field of this quantum machine learning domain. And finally, one of the most promising areas is applications of quantum algorithms on quantum data from some quantum experiments. So these are just some examples of quantum algorithms, most popular quantum algorithms like QAOA, quantum approximate optimization algorithm, or variational quantum eigensolver. So these are the so-called variational algorithms in which we have a specific quantum circuit that is parallelized, and also parameterized, and we can potentially adjust the parameter of this circuit using machine learning methods. So for example, using gradient descent. So we can potentially train this quantum circuit in order to find the value of the parameters of this quantum circuit that will help us solve our problem, right? So for example, to minimize the loss function or the cost that we have. So I've already presented an example of a rotation gate that was parameterized, right, by a single parameter. So we can, in a similar way, we can parameterize many quantum gates in a given circuit and then try to train such an algorithm to just solve our task. So this is quite a natural application of these variational algorithms, right? So for each value of such a parameter, we can just run many instances of measurements to many measurements and calculate the average values and stop once we achieve the minimum value, let's say. All right, so it's good to know that there is an interesting progress in quantum computing observed recently, especially during the last 5 years. So we now have better and better quantum computers, and there are also some interesting programming frameworks allowing us to write code that can be run on quantum computers. It's hard to say what might be the future of quantum computing because there are still some obstacles on the road toward quantum supremacy, like the issue of the coherence or error correction. Even from the algorithmic perspective, sometimes it's difficult to prove that quantum algorithms will be better than classical algorithms. And also building some quantum gates is still challenging. But it's good to know that we can already write some quantum programs and also programs implementing quantum machine learning algorithms. So here is just an example. It's a simple circuit just prepared using PennyLane library. It was the first library for quantum machine learning, so it was called the TensorFlow of quantum computing until Google released a similar library that's called TensorFlow Quantum. So it was an extension of TensorFlow in order to just allow to write quantum machine learning programs as well. Another quantum machine learning program is and framework is Qiskit ML, so it's machine learning model for Qiskit. Qiskit is one of the most popular programming frameworks for quantum computing. It was developed and released by IBM. If you would like to learn more, there are some interesting resources available on the internet. I especially recommend the lecture and the book authored by Maria Schultz from Xanadu. You can find some interesting resources on the website of my Quantum AI Foundation, and I also recommend the lectures on quantum machine learning given by Peter Witek. So I thank you for your attention. If you have any questions, feel free to reach me out. And I'll be happy to answer. I also invite you to visit the website of the Quantum AI Foundation just to stay in touch and read about our activities like workshops, lectures, conferences, hackathons, and contests. If you like our activities, you can also donate. So I hope that you enjoyed this lecture. I wish you good luck and all the best in your quantum computing education. And I hope to see you on some events, meetups organized by the Quantum AI Foundation. Thank you.
All right. Hi, hello, and welcome everybody once again. This time, welcome to Q&A session. I would like to ask the technician to also give the floor to Paweł, our speaker. Yes, we've got Paweł here. Hello, Paweł.
Hello, Jędrzej. Hello, everyone.
Awesome to have you here live. We've got, as far as I can see, 4 questions right now to you. And let's start with the most upvoted one. So the first question asked by Adam. Would you agree with the statement that a real quantum computer has not been created yet? Then, how far are we with the state-of-the-art solutions from the commercial quantum computer?
Okay. So as far as I know, I think that the real quantum computer has been created. So there exist real quantum processors, but the problem is that they are not as powerful as classical computers. And it looks that we are still some distance from the state of classical computers. So we'll have to wait for some time for the real world applications in which quantum computers will be able to just outperform classical computers in practice, but some real quantum processors have been already created and are available, for example, in the cloud. So that's the answer to the first question.
Okay, and the second question asked by Philip: what is the physical reason that we have only the zero higher or one state in classical computers? 0 and 1 are simply voltage or no voltage.
Yes.
Do you understand the question? Yeah.
Could you maybe repeat? Because
yes, I will also paste it to the chat maybe, because
okay,
I'm not sure how to read it out loud with these states, but yeah. Right.
Okay, so there's a does quantum machine
that one, excuse me.
Yes, is it okay? I can see one question on chat.
And that's the question I was actually that was the question I was
okay. What are the physical reasons? So potentially maybe we could think about having more states, right? Because quantum mechanics allows us to have more states, but I would say that it's not a physical reason, but it's a computational reason, right? That we already represent data using bits, in which case we have just two values, right? And also in some cases, when we run computations, it might be also easier to just obtain these states 0 and 1 after the measurement. So for example, zeros and ones may correspond to spins of atoms, right? So after the measurement, we can just get state 0, 0 or 1. But before we do a measurement, we may consider many other quantum states, many other possible quantum states of a single qubit. So it's just a matter of how we interpret the results, in fact. So potentially we can also think about a single logical qubit that can be built using many physical qubits. And in such a case, the logical qubit may have more than two states, right? So for example, one logical qubit can be composed of, for example, three physical qubits. And in such a case, we could have, let's say, 8 states, for example. So it can be also possible. So I would say that one thing is that it's easy to just measure some values, some physical properties like spins, in which we have two values. So this is, I would say, the physical reason. And there is also computational reason that we are also used to just storing data in bits when we have two values.
Thank you. The next question asked actually by me. In your opinion, what is the most important element of quantum computing or quantum machine learning whose decisive development would be crucial for the growth of the entire field?
Could you please repeat once again, because there were some technical issues?
Yeah. In your opinion, what is the most important element of quantum computing or quantum machine learning whose decisive development would be crucial to the growth of the entire field?
All right. In my opinion, definitely quantum hardware, because I believe that we already have some quantum algorithms that are pretty good. So we cannot say that we know many quantum algorithms that will give us advantage or provable advantage comparing to classical computers. But as far as I know, The biggest issue now is with the hardware side. So to build really powerful, larger quantum computers with more qubits and with lower noise.
And last, actually, we have one more question. So let's maybe go with this one from Kacper. Could you give an example of a current application of quantum machine learning frameworks?
Okay. Yes, I can give. So in general, this quantum machine learning, the existing quantum machine learning algorithms can be used, for example, to help in solving combinatorial optimization problems like the traveling salesman problem. So if someone is interested, I can also give some references to the papers on this topic. And also, I've read some articles about enhancing computer vision methods, enhancing even convolutional neural networks using quantum computing as well. And the results were not better than in the case of classical computers, but let's say that the accuracy of such quantum machine learning algorithms were on par, so more or less on the same level as in the case of classical computers.
Awesome. I think that concludes. Thank you very much, Paweł, for your participation, and hope to see you later in the conference. Thank you.
Thank you. Thanks. Bye-bye.